For all seafarers, weather has a large impact on their lives at sea and on the safe passage of their ship. A greater understanding of weather patterns can play a key role in ensuring safer voyages with fewer delays. In this two-part training package, we shall look in Part 1 at how weather systems are generated, and in Part 2 at how ships can best adapt to different weather conditions. The videos, which are accompanied by a booklet, are modular, and we recommend you watch one section at a time. The Earth has a mean diameter of 11,040 kilometers, and the atmosphere which surrounds it stretches up a mere 480 kilometers, and it is only a tiny 16-kilometer lower layer of atmosphere, the troposphere, which has an effect on weather. If the Earth was the size of a grapefruit, this lower layer would be the thickness of just one sheet of tissue paper. All the weather is generated within this thin lower layer. During the 1990s, weather was the major cause of 30% of all ships considered a total loss by the insurance industry, by far the biggest single cause. During this decade, the number of serious incidents hardly altered, and the number of seafarers killed or missing due to weather-related incidents sometimes reached horrifying proportions. The number of incidents involving pollution was on a worryingly upward trend, and the number of ships lost also remained high. Of course, the problems of bad weather are familiar to all experienced mariners.
I just joined this ship in Trinidad. We were sailing northbound. We got word of this storm just north of Bermuda. Gearless bulk carrier. She only had about 6-7 feet freeboard, and we hit these waves that were absolutely enormous. I've never seen anything like it since. I reckon they were probably between 50 and 60 feet high. Certainly when you were in the trough, you could see these waves, and they were absolutely level with the bridge wing. Did result in quite a bit of damage to the hatches. One of our hatches, I remember, sank by about 6 inches. When we got to our destination, we found it had dropped 6 inches. The weather lasted for about 2-3 days, and we were actually driven in the reverse direction to which we were heading, almost 200 miles over a 24-hour period during that storm.
Avoiding bad weather at sea may help to save lives, but there are strong commercial benefits as well. With your ship on a tight schedule, it may seem strange that slowing down or taking a longer route will save money. But if there are storms ahead or other weather problems, that is indeed the case. To avoid the worst weather, navigating officers must understand what weather forecasts say and how they are produced. If the Earth's surface was uniform, the weather would be much more stable and predictable. It is because the areas covered by land and water heat up at different rates that weather patterns are established. The Earth is heated by the sun. The areas near the equator receive the greatest amount of energy because the sun's rays arrive almost perpendicular to the surface, and therefore have a shorter passage through the atmosphere. So the surface in these regions is heated the most. At the poles, the sun's rays arrive at a shallow angle. They need to pass through more atmosphere and will therefore lose more of their energy through reflection and scattering effects. The remaining energy will also be spread over a greater surface area. Pressure is defined as force per unit area. So the air pressure at any point on the globe is proportional to the weight of air standing in a column above that point. Remembering that the atmosphere extends upwards about 480 kilometers, even a light gas like air will exert significant pressure on the surface. As one moves vertically upwards through the atmosphere, the air pressure steadily decreases. When part of the Earth's surface is heated, the air next to the surface becomes warmer. It expands on heating, and at an upper level it exerts a greater pressure than air in the surrounding areas at the same upper level. It naturally pushes out towards the areas of lower pressure, and a circulation is established. The falling, cooler air in adjoining areas exerts a comparatively higher pressure at the surface. So, areas at the surface with rising warm air are associated with low pressure, and those with descending cold air with higher pressure. On a planet with a completely uniform surface, the circulation of the atmosphere might be like this, with mainly low pressure near the equator and relatively high pressure at the poles. But the Earth has two particular complications. It rotates quite quickly, and there is an unequal distribution of oceans and land masses. The net effect is that there are three generalized circulations in the atmosphere. Having risen above the equator, warm air moves towards the poles, but having cooled somewhat, starts to descend at around 30 degrees latitude, giving rise to a belt of mainly high pressure. At the polar regions, cold, heavy air descends, and that circulation is completed by air rising at around 60 degrees latitude, from a region where low pressures predominate. In between these two circulations is a third circulation that flows in the opposite direction to the others. This represents an area of cyclonic disturbances. The general pattern is repeated in the southern hemisphere. The picture is further complicated by the uneven distribution of the major land masses. Particularly in the northern hemisphere, most of the land is found in the mid-latitudes. Land heats up more easily than water. Therefore, the generalized picture of surface air pressure is more like this. During the northern hemisphere's summer, there is low pressure at the equator and centered over the hot land masses, high pressure over the oceans and the colder land in the southern hemisphere. During the southern hemisphere's summer, there is low pressure at the equator and over the southern land masses, high pressure over the southern oceans and the northern land masses. It is these differences in surface pressure which give rise to one of the main characteristics of the weather: the wind. The prevailing winds move over the ocean from areas of high to areas of low pressure. They would generally follow a pattern like this, with winds converging on the low-pressure equatorial zone and on the mid-latitudes, with slight variations according to the season. But the Earth's rotation provides a second complication. This causes the winds to be deflected due to the so-called Coriolis effect. The best way to think of this is as follows. Imagine a body of air at a certain latitude. It has a certain angular momentum because the atmosphere of which it is part rotates with the surface of the Earth beneath. Now imagine this body of air is forced to move due north, away from the equator, because of a difference in surface pressure. As it moves north, its distance from the Earth's axis of rotation would decrease, as would its velocity around the axis. But any freely moving body always preserves its original momentum, so its angular velocity must increase compared to the Earth beneath. It therefore veers to the right.
If the body of air was being forced to move south, the opposite occurs. At the start, both angular momentum and velocity around the axis are relatively low. As it moves south, its distance from the axis increases. But for its angular momentum to stay the same, it needs to slow down compared to the Earth's rotation. Again, it veers to the right. In the southern hemisphere, the same principle applies, but in reverse. Winds deflect to the left as they move towards the equator, and also to the left as they head for the pole. In the equatorial region, where change in latitude has virtually no effect on the distance from the axis of rotation, the Coriolis effect is negligible. There are, of course, many local variations, but the prevailing winds are: in the equatorial region, up to latitudes of about 30 degrees, the northeast and southeast trades, and in the mid-latitudes, mainly westerlies.
This tendency for winds to deflect increases with latitude, so some weather charts incorporate
The geostrophic wind scale,
which relates the spacing of the isobars and the latitude to the wind which is produced.
The geostrophic wind is the actual wind blowing at a height of about 600 meters. It starts blowing from high pressure straight towards low pressure, but is slowly bent round as a result of the Coriolis effect until it remains parallel to the isobars. At the surface, due to friction, the wind speed over the sea may be half to two-thirds of the geostrophic value. And because it is moving more slowly, the Coriolis effect is reduced. The wind's direction is about 10 to 15 degrees in towards the low pressure. The air in the atmosphere has low thermal conductivity and is not subject to constant mixing. So areas which are mainly cold tend to stay cold. Those which are warm stay warm, and those which are hot stay hot. So we talk about different air masses with quite abrupt boundaries between them. The air masses do move, but slowly. Their temperature and humidity depends very largely on where they originate. The principal air masses are Arctic maritime air, which originates over the sea areas near the poles. This will be very cold, and so the moisture content is also low. Arctic continental air, which originates over land masses at the poles. This is also cold and dry. Polar maritime air. Despite the name, this air originates over water in subpolar regions. As it moves to more temperate latitudes, it will gather moisture and become unstable, typified by cumulus clouds and squally showers. Polar continental air originates in the subpolar regions over land and is cold and dry. In winter, if it moves over relatively warm sea, it will start to resemble polar maritime air. Tropical maritime air originates over seas in the subtropics and is therefore warm and very moist. It tends to move towards the temperate latitudes, and passing over cooler water will often give rise to fog. In summer, if it passes over hot land, this air becomes unstable and often gives rise to showers and thunderstorms. Tropical continental air starts off hot and dry. It is likely to pick up some moisture when passing over seas, but not enough to trigger precipitation. Equatorial air is very warm, moist and unstable. Passage over hotter land areas will produce cumulus and cumulonimbus clouds to a high level and rainfall in large quantities. The movement of major air masses is usually slow and predictable. However, polar maritime air, after being warmed in its lower levels, sometimes turns back towards higher latitudes and assumes the characteristics of tropical maritime air. Then it is called either warm polar maritime air or returning polar maritime air. The boundaries between the air masses are the frontal zones: the Arctic front, between Arctic air and polar air; the polar front, between polar air and tropical air; and the narrow intertropical convergence zone, or ITCZ, where equatorial air lies between areas of tropical air. The mean position of the frontal zones moves up and down the globe, according to the season. When these large air masses, with quite different characteristics, meet, interesting phenomena can occur at their boundaries, and it is here that a lot of what we call weather arises. Where two air masses meet, the abrupt transition is known as a front. Where a warm air mass meets a cold one, it tends to ride up over it, being composed of less dense air. For example, the polar front, where cold polar air meets warm temperate air, will be wedge-shaped in cross-section like this, though in reality the slope of the boundary can be as shallow as 1 in 200. Being deflected by the Coriolis effect, the two air masses slide past each other in opposite directions. This situation would remain stable except for conditions at high altitude. If there are narrow and concentrated high-speed winds, the jet stream, in the same locality, they tend to suck air up from the lower level. Consequently, a low-pressure area starts to form at the surface, and winds flow in to restore the balance. The warm, moist air spirals up, giving rise to clouds and precipitation, and the latent heat released by this intensifies the whole process. The cyclonic rotation is anti-clockwise in the northern hemisphere, clockwise in the southern. The intrusion of warm air becomes more pronounced, with the heavier cold air pushing down the flank. A distinctive warm sector is formed. Localized pressure continues to fall, and the familiar depression is born. It is characterized by isobars forming closed loops and is moved along the line of the polar front by the jet stream winds at the upper level. Usually, a cold front moves round more quickly than the warm front because it is the leading edge of cold, denser air pushing up the warmer, lighter air. So a warm front advances at 30 to 50 kilometers per hour, say from 17 to 25 knots, while a cold front can move forward at 60 to 80 kilometers per hour, about 35 to 44 knots. In overtaking the warm front, it forms an occluded front, which means that the sector of warm air is no longer in contact with the surface. As we saw before, at the surface level the winds bend in at an angle towards the low pressure. The circulation of winds around a depression in the northern hemisphere is anti-clockwise. In the southern hemisphere, it is clockwise. This fact is conveniently expressed in Buys-Ballot's law, established in the mid-19th century. If a mariner stands facing the wind in the northern hemisphere, the pressure is lower on his right-hand side than on his left. In the southern hemisphere, if he stands facing the wind, the pressure is lower on his left-hand side than on his right. Not all depressions are associated with fronts. Thermal depressions occur where there is unequal heating of land and sea surfaces and little wind. For instance, an island or peninsula in the tropical summer will heat up relative to the surrounding waters. Air will expand vertically, giving rise to relatively high pressure at the upper level and sideways spreading. The air column over the peninsula is now less heavy, so there is low pressure at the surface. A circulation is established. As the air which flows inwards is moist, thunderstorms and squalls may be expected. The release of latent heat of condensation further stimulates the system. A polar or instability depression is a secondary depression which arises in the wake of a frontal depression. The cold polar airstream is being dragged over relatively warm ocean. Water vapour condenses, and again the latent heat of condensation causes air to rise and produces low pressure at the surface. Instability depressions are often less than 200 miles in diameter and may well arise in areas not well covered by observation. So they may not show up on weather forecasts, but they are important because a secondary depression can sometimes intensify and become much more vigorous than the primary depression it is replacing. The most important type of non-frontal depression is the tropical revolving storm. This represents some of the worst weather conditions a seafarer is ever likely to encounter, being smaller and usually much more intense than a frontal depression.
Hurricane, typhoon and cyclone are all local names for tropical revolving storms.
We hit a typhoon just to the south of Japan, and I'm not sure whether it was our fault in navigating incorrectly or whether it was the typhoon had actually changed direction, but we went right through the eye of this typhoon, or rather the eye of the typhoon went right over us. That was quite incredible, because as we approached the eye, the storm was obviously blowing, I would say, in excess of force 12. Completely white as far as visibility was concerned, white outside, just spray everywhere. Ship rolling horrifically, pitching horrifically. We passed through this wall of water into the